Hope things are going well. Hope nice weekends were had. As a brief reminder, last week we finished the content for chapter 17, which was about circuits, voltage, resistance, current, and power. A lot of things piled into one. Let me know how working on the homework and such was for that over the weekend. Let me know if you have any questions. Main item on the agenda for this week is magnets. Talking about magnetic fields, magnetic forces, and some of the weird ways that magnetism and electricity relate and connect to each other. The chapters, I guess, plural, that this is going to cover, because we've kind of been, at this point, we're going to kind of be skipping selectively around the textbook that this course is originally based on. The actual numbers don't really mean much for the sake of this class, but basically, since we're picking and pulling selective magnetics concepts out of chapters 19, 20, and 21, the numbering for the upcoming notes and the upcoming homework and stuff will just reflect that. It doesn't mean more work, it just means that's where it came from in the original source book. It still will be the same amount of work, same amount of content as previous chapters. So this week is magnets. Next week, after we wrap up magnets, we'll review everything electricity and magnetism we've talked about so far. And towards the end of next week, we will transition into test 2. So that'll be at the tail end of next week. I would say I'd probably make the test live around the 27th or so. And then you guys would be able to take it whenever you want, kind of like the last one. After that test is in and grades are in, we will cover like a few more days of small concepts, because the syllabus does list light and waves on it. Light and waves are a good thing to know about, just because that's how, at least light and waves are good to understand, because it helps it is Monday and I can't talk yet. Forgive me. Let me rewind. Magnets this week. Next week we'll transition into test review, and then having test 2. Week after that we will talk a bit about light and waves, because they're good things to understand, and then we will transition into our final exam. I think that's August. It'll be in August. First week of August. So things are winding down. I've only got a few more weeks left. As we're approaching the end, it is of utmost importance that you let me know whenever you have any issues, needs, questions, concerns, etc. The sooner you let me know about them, the faster I can help you with them. So do keep that in mind. All right. Additional reminder, we do have lab this week. I'm still planning exactly which ones we're doing, so stay tuned for information about that, but there will be lab assignments this week, just to keep that on your radar. All right. While I get set up for presenting the magnets notes, please, again, tell me if there's any questions or needs that you have. All right. So, magnets time. Now, magnets and magnetic field and magnetic phenomena are related to electricity. They are related concepts, but they are not the same thing. When we talked previously about electric charge and the force between electric charges, that is not the same thing as the force between like physical bar magnets that you might own. Magnetic force and electric force are different concepts, but they are related concepts. It's kind of like how... Wow, I don't have an analogy for that off the top of my head. Oh, here we go. It's kind of like how the two sides of a coin are two distinct sides. They may have two distinct pictures on it, but they're still a part of the same coin. Electricity and magnetism are literally two halves, two opposite faces of the same coin. I might have mentioned a while back when talking about fundamental forces that there's 4 fundamental forces that hold the universe together. Those being the gravitational force, the electromagnetic forces, strong nuclear interaction, and weak nuclear interaction. Of those 4 forces, the second one, the electromagnetic forces, are technically a family of forces, plural. The electric force and the magnetic force, again, are sort of opposite sides of the same coin. They are different things, but they are related. Kind of similarly to how the electric forces operate similarly to gravitational forces. If you recall us comparing the formula between universal law of gravitation to Coulomb's law, looked at the similarities in their structure and how they work, and the similarities between gravitational fields and electric fields. As we start looking at magnets, magnetic forces, magnetic fields, I'm hoping that it should become clear that electric fields and magnetic fields are even more alike than either of them are to gravitational fields. So, magnets are their own unique, distinct phenomenon. They are separate but related to the electrical forces. So, magnetic fields are similar to electric fields and electric forces in that a magnetic object, an object that has magnetic properties, does create its own field of this new specific type. It creates a magnetic field. And magnets, well, looking at the image here on screen, just to start with, because this is at least partially what a lot of people think of when they hear the word magnet. This is just a bar magnet here. And bar magnets, as you might have used in the past, or you might have seen visualized in things, have a north pole and a south pole. Magnetic fields come out of the north pole end and move into the south pole end. This is similar, not identical, but similar to how electric fields come outwards from positively charged objects and inwards towards negatively charged objects. But note that there is still different terminology here. Magnetic fields go from north to south. Electric fields go from plus to minus. They are different fields. They have different terminologies for that reason. So, magnetic objects give off magnetic fields, like how electrically charged objects give off electric fields. These magnetic fields, when they always bend from north to south, and they always, whenever magnetic field lines from two separate fields overlap with one another, that's when you get magnetic force between two magnetic objects. If you physically have two separate magnets and you bring them close together, their magnetic fields will physically overlap, and that's when the force interaction between the two occurs. Like how, when electric field lines overlap and clash, that's when you get electric force between two charged objects. So again, similar, but different terminologies so far. But they're similar in their shape, they're similar in their function. There is one important thing to note about magnets, though. And it's that you can never have an isolated north magnet by itself, and you can never have an isolated south magnet by itself. Notice here in this picture, this one bar magnet has a north pole and a south pole. If you were to try to chop this magnet in half, you wouldn't get one separate north end and one separate south end. The two halves would now each have their own north pole and south pole. Unlike electric charges, where single sign isolated charges can exist, you can have just protons that are just positive, you can have just electrons that are just negative. Magnets can never just be one isolated pole. They have to come in a pair. They have to. Now, moving on. We'll use Earth as a comparison. You've probably heard by now of Earth's magnetic field. It goes from the North Pole, the physical Earth North Pole, to the physical South Pole. And Earth's magnetic field is very important. It's a field that surrounds the planet, and we kind of treat it as if there's a giant bar magnet in the planet creating the field, and so the diagram looks, the field diagram looks similar to the picture from the previous slide. And Earth's various magnetic properties create this field that goes from one pole to the other. Earth's magnetic field is incredibly important, and this should serve to demonstrate that magnetic fields are not the same thing as electric fields. Earth definitely has a magnetic field, and that field does exert its own specific magnetic properties. But if it was an electric field instead, then it wouldn't do a bunch of the things that we need it to do or expect it to do. Electric fields exert forces on electrically charged particles. And so if Earth's field was electric instead of magnetic, every single loose electron on Earth would start drifting towards the positive pole, positive charged end. It wouldn't really be a pole. Similarly, if Earth's field was electric instead of magnetic, it wouldn't make compass needles point, because compass needles are specifically reacting to a magnetic field in order to move them around and point in a certain magnetic direction. I'm just now realizing how noisy my puppy's chew toy is. I apologize. Annie. It was noisy for me. Not sure if it was picking up on the microphone. If it was an electric field, it wouldn't make that pointer of the compass move the way that it does, because most of the time, most objects are neutrally charged. It takes effort to charge it up to where it will respond to electric fields. Whereas magnetic fields just inherently react to all objects that are capable of reacting to them, including the lodestone of a compass needle. So I'm going over this to try to help differentiate, again, between magnetic fields and electric fields. They are quite different things, related but separate. Earth's magnetic field specifically, interesting fun fact. For one thing, Earth's magnetic poles don't line up with the geographic poles, but that's something that I think a lot of history and science classes might have covered at some point in your past curriculum. What a lot of people don't quite know is in addition to the magnetic axis of the planet being tilted from the geographic axis, the north geographic pole is actually closest to the south magnetic pole. We do have a magnetic pole roughly, up and down, bisecting the planet near the geographic poles. But even though geographic north is in this direction, technically the pole that's up there right now is the magnetic south. And so when your compass needles point north, what they're actually doing is pointing south, and the other end of the needle points north. It's kind of a mess, and it's to do with the fact that, I assume it's to do with the fact that European settlers just assumed, oh, north is north, it has to be north, we're calling it north because we live in the northern hemisphere. But it's further complicated by the fact that occasionally Earth's north and south poles just kind of swap sides. We have some evidence to indicate that once every millennia or so, the poles just swap directions suddenly. Suddenly the north magnetic pole becomes south and the south magnetic pole becomes north, which, when it happens, shouldn't do anything catastrophic. We just have some evidence that it does happen. And the fact that that happens and the fact that we don't fully understand why it happens, or frankly the fact that we don't really understand why Earth has a magnetic field in the first place, not completely anyway, should give you an idea of why magnets are kind of still a mystery, even to physics. Physicists have done a lot of work over the years to try to quantify magnets, to understand magnets as best as we can, but there's a lot about magnets in general that we still don't know. It's one reason why this is a meme. You can pretty much blame anything in science on magnets, and no one can really dispute it because we still don't really understand it in their entirety how magnets work. We know that they create magnetic fields. We're just not always certain why they make magnetic fields. Especially the Earth itself. We have hypotheses as to why Earth creates a magnetic field, but we aren't really certain why Earth creates a magnetic field. It's a good thing that we have one. Life wouldn't quite be possible on Earth without that magnetic field, but why it's there, exactly how the planet makes it, is as much a mystery as most other things about magnets are. Now for this class, we're going to go over the stuff that we have absolutely quantifiably measured about magnets. We're going to focus on the things we do know about magnets. I'm going to focus on the numbers that we can measure about magnetic fields and the effects that they have. That's what we're going to be focusing on. But if you ever want to make a scientist agitated, if they're talking about their work, if they're talking about their research, just ask them how their work is affected by magnetic fields. And 9 times out of 10, they don't have an answer. So that was a bit of a tangent. I like talking about how weird magnets are. So, electric fields and magnetic fields are separate phenomena. One can exist without the other. Bar magnets make magnetic fields, Earth's magnetic field exists, and they don't necessarily create electric fields. They're separate things. Magnetic fields interact with magnetic fields, electric fields interact with other electric fields and charged particles. But remember how I said magnets were weird. I'm going to keep coming back to that statement. Magnets are weird. And one of the reasons that they're weird is not only do magnetic fields interact with other magnetic fields. If you put 2 magnets near each other, there's going to be some force between them. North poles will repel, like poles will repel, and opposite poles will attract. So that adage from before is still useful. But one of the weird things about magnetic fields is that they do affect the motion of charged particles. Magnetic fields can exert force on electrically charged objects. Keep in mind, electric fields and magnetic fields are different things, and yet still, magnetic fields can exert force on charged objects. For example, there's currently a picture here on screen, and I'm going to try to make it bigger to illustrate exactly what's happening here. Move the text out of the way. So, the image that's currently on screen right now, it's something of a vacuum tube scenario. Here we have a sealed glass bubble. This is a large glass sphere. And within this glass is an electron stream. This little thin blue wisp of light What's actually happening here is electrons are being fired through this glass enclosure from this emission side to the other side over here. So electrons are physically being fired across the width of this chamber. And the reason that you can see blue light as those electrons move through here is because there is air in the chamber, and kind of like how you only see electricity because the electrons energize air, here the moving electrons energize air, and you can see the light the air gives off. So the blue light is given off by air that electric current is moving through. And hopefully, my intent is, if you look closely on this picture, you can notice that this blue wisp, this blue line that represents the motion of the electric current through this chamber, isn't straight. It's not a straight line. In fact, it's actually curving partway through. You can see how it kind of moves in a straight line, but then it starts bending down, and then it starts bending up. The reason it's bending is because of these two objects up here. Those are magnets. Those are physical bar magnets exerting their magnetic field into this particular chamber. Now, the electrons moving through this aren't magnetized. They're just normal electrically charged, negatively charged electrons. But they're moving through the magnetic field created by these bar magnets. And I'm just going to, for simplicity's sake, I'm going to call this north and call this south. So these electrons are moving through this magnetic field. When charged particles move through an electric field with some velocity, they have to be moved. I think I stumbled over my words there. When charged particles move through a magnetic field, the magnetic field is able to exert a force on those charged particles as the particles move through it. And so here in this picture, the goal is that you should be, I'm hoping you can tell, the charged particles here, their trajectory is warping in a few different directions because they are moving through this larger magnetic field. The path they're on, their velocity vector is changing directions because the magnetic field is exerting force on those electrons. So this is, I'm hoping, proof, or at least an example, of how magnetic fields can affect the motion of electrically charged particles. Now, we do have a formula to describe this phenomenon. Is it on this slide? It is. So, magnetic fields exert magnetic force on other magnetic fields. They exert magnetic force on certain materials that are able to align themselves to magnetic fields. For example, iron is ferromagnetic. That's a term for the type of magnetism that iron has. A chunk of iron by itself does not create magnetic fields, but a piece of iron does react to magnetic fields. We think this happens because its particles, its electron and proton structure, when exposed to a magnetic field, its own particles align to that field, and it's in that moment it is allowed to, one, be subject to magnetic forces, and two, create kind of a small magnetic field of its own until it's removed from the other magnet, and then it just goes back to normal. So there are objects that themselves don't make magnetic fields normally that magnets can still affect, like, again, iron, compass needles, etc. But weirdly, and one of the things we're going to focus on for this particular week of class, is how magnetic fields affect the motion of electrically charged particles. So, the formula for what I just described is right here on the screen. The force that a magnetic field will exert on a charged particle moving through it is equal to the magnitude of charge of the particle times the particle's velocity times the magnitude of the magnetic field. So, couple things to unpack here. First, let's focus on this B variable right here. My handwriting's atrocious, I apologize. So, within this new formula, the B variable represents the magnetic field in question. So, capital uppercase B is the variable for magnetic field. It's going to show up in a lot of formulas this week. B is magnetic field. Sometimes I might refer to it as a B field for that reason. That's a common way of describing it, as a B field, as opposed to an electric field's E field. And it works pretty similarly to an electric field. The field gets weaker the further you go away from its force. The field exerts forces on specific objects or specific fields within itself. And B is just the variable for magnetic field. The unit for magnetic field is Teslas. You've probably heard the name Tesla before in reference to the scientist Nikola Tesla. In this specific context, it's just the unit of the strength of a magnetic field. The stronger a magnet is, the bigger the magnetic field it gives off, the more Teslas it gives out. So Tesla is just the unit for magnetic field. So this formula tells us that if a charged particle, Q, is moving, V, through a magnetic field, then the field will exert some amount of force on the particle in question. This is what we again see here in the picture. You have charged electrons trying to move through a magnetic field. They have some velocity, they have some charge, the field has some strength B, and therefore the field will exert some force on them, and that force is going to force on an object with mass will accelerate it. That force is going to change the direction of and kind of deflect the moving electrons in this particular case. And that's why the light in this picture changes directions. You can see it bending down and then up, as the force from the field literally pushes it in different directions. So this is our first magnet formula. It's pretty straightforward. It only has one new variable in it. Couple things to note about this. One, the velocity of the charged particle is important to the actual amount of force that the field will exert on it. Note that that V term is right there in the numerator with everything else. If we were looking at this same apparatus and we weren't firing electrons through it. We just have electrons sitting in the bubble and we turned the magnets on. If those electrons weren't moving through the field, if their velocity was 0, then there wouldn't be any magnetic force on them. This formula, this concept, only creates force on the charged objects when they are moving through a magnetic field. If they're stationary, then there's no force. If they are moving, though, that's when the magnetic force activates. And that's why here, in this particular chamber, as the electrons are moving, you can see them bending because they're moving, and because they're moving, you're going to get a non-zero force. But normal, roughly stationary electrons don't have any force acting on them from any magnetic field. And this is, thankfully, well, it's a good thing that's the case, because if the magnetic field was always exerting a force on charged objects, then Earth's magnetic field would constantly be scrambling your body's own electrons. It's only when they are moving, it's only when they're in the form of electrical current with a velocity that the magnetic field exerts force on them. So, in a weird way, magnets can deflect electricity. Magnets can exert a force on electric current and make that object move out of the way. So, that's one of the two quirks. This formula only works when velocity isn't zero. If velocity is zero, there's no force. If velocity is not zero, then there's some amount of force. The other quirk to be aware of here is, note the perpendicular symbol attached to the velocity. The velocity and the magnetic field need to be perpendicular to one another for there to be a force between them. So not only does the particle have to be moving, it has to be moving perpendicularly to the field lines. I'm going to kind of redraw this picture here. So North Pole, South Pole, field lines between the two poles. And if I switch colors to represent the velocity vector, note here, in a very rough approximation of what's happening in this picture, we've got the magnetic field going up and down. We have the charged particles being fired horizontally to the right through the field. Note that whenever the velocity line intersects with the magnetic field line, the lines are perpendicular. At any given one of these intersections, the velocity is completely, or at least mostly, perpendicular to the magnetic field lines. And so this is the situation that does create magnetic force. If the magnetic field lines were running horizontally, and the particle was also moving horizontally, then nothing would happen. Nothing would happen in that particular context because the formula requires V and B to be perpendicular. If they're parallel, then then the perpendicular component is zero because there's no perpendicular component. So the formula only gives you a non-zero answer in this case when the field and the velocity vector are perpendicular to one another. So that's the second quirk of this formula. First one was you have to be moving. Second one is that you specifically have to be moving perpendicularly to the field lines. The third quirk of this formula is trying to understand what direction the force is ultimately going to point in. Again, magnets are weird. They're mysterious. Magnetic fields do very strange things. The fact that magnetic fields work at all on just normal electrically charged particles is kind of bizarre. But what I think is the weirdest part about it is, again, we've already noted that in order for there to be any magnetic force on the electric particle, the B field and the velocity need to be perpendicular to one another. They don't necessarily have to line up with the x and y axis, but they need to be perpendicular to each other for there to be a force between them. The weirdest thing ends up being what direction that force points in. In this specific case here, the velocity vector points, the way that I just drew this image, velocity vector points to the left, magnetic field points up. So what would your first guess be about what direction the magnetic force would be? And you would not be faulted for thinking it could be something in the x-axis or something in the y-axis, because those would make sense. We've already got forces in the x and we've already got stuff in the x and stuff in the y. Why wouldn't it be in those two axes? Or maybe like, halfway between those two axes. All of those things would make an amount of sense. What the magnetic field actually does, the actual direction that the force points in, is in neither the x nor the y-axis. I'm going to draw a different well, no, I'll just make this a 3D image. The force actually, if this is the x, I'm going to use a different colored ink for this part. If this is the x and this is the y, the force would point in the z-axis. We haven't really done math related to the z-axis in this particular class. We've acknowledged the fact that we live in a three-dimensional world, but we haven't had to do any math involving that third axis, that z dimension, yet. And we're not going to do a whole lot of complicated math about it. What we're mostly here to do right now is just acknowledge that the velocity, the magnetic field, and the resulting force are all perpendicular to each other, and the only way that happens is if they are all three in the three different axes, x, y, and z. Now, the way that I and a lot of people try to remember this is using something called the right-hand rule. I might have mentioned it kind of briefly in the past in reference to... When did I talk about it? Did I only mention it for screws? Not important. I think I've mentioned it in passing in lab once. Electrically speaking, in this specific context, for the magnetic force acting on charged particles, what the right-hand rule can help us do is to keep straight in what direction the velocity vector, the magnetic field vector, and the magnetic force vector are all pointing. And the reason that your right hand is useful for this is that different parts of your right hand can point in those three different axes at the same time. So if you take your right hand and you hold it kind of like you're doing, just hold it open almost like in an L shape, then your thumb points in one axis, your fingers point in a different axis that is perpendicular to your thumb, and then your palm points outwards in a third axis that's perpendicular to both of the previous two. So your hand can represent those three different axes at once. Your right hand specifically shows the perpendicular nature of how those three vectors can intersect. So the rule goes, if you point your fingers, like you're literally pointing in the direction that the electric current is flowing in, the direction the protons or the electrons are moving in, and you point your palm in the direction of the magnetic field, I'm a comics nerd, so when I'm doing this, I tend to think about like Iron Man blasting stuff out of the palm of his hands. So you point for the current, you blast the magnetic field out of your palm, so those two things are perpendicular to one another. That fulfills our requirements. Velocity is perpendicular to the magnetic field. Then once you've done those two steps, your thumb, perpendicular to both of those other two, will point in the direction of the resulting force. So current goes to my right. I'm not entirely sure how you're seeing it on your screen. Current goes to the right. Magnetic field points into the camera. In that situation, the magnetic force would point up. It's kind of weird. It's very weird, I will admit. It's very weird. It takes some practice to A, understand, and B, even try to be able to use this information. So we're going to look at some examples real quick to try to get in practice of using the right-hand rules. But again, full admission, magnets are weird. I'd say out of all the chapters of this class so far, of any chapters you might have ever covered in physics, magnets are allowed to be the weird one. They're allowed to be the hard one. When I was taking my physics classes to get my physics degree, my electricity and magnetism class was probably my least favorite because of some of the nonsense about magnets and magnetic fields. This is allowed to be weird. This is allowed to be tricky. We've got time to talk about it. So, let's look at a few rapid-fire examples. Now, 3D pictures are kind of hard to draw. Whoops. I think I lost signal for a second there, but I didn't stop. It didn't stop my screen share, which is good. Let me know if you think you missed something. I didn't start the... There it is. So, we'll just real quick kind of use the right-hand rules on each of these cases to figure out what direction the force points in. So for part A, the particle's velocity points to the right. I don't actually know how my camera orientation is going to display this, so forgive me if it's backwards. Particle velocity points to the right. The field is going to point into the page, and so the direction of our thumb in this case would be straight down. So velocity, field, force is downwards in this specific one. For part B, the particle velocity is going to point to the left. The field points up. So you'd think then, looking at the direction of our thumb, that would come out of the page. The force in this particular case will point... Actually, wait. My mistake. It would be into the page the way that I'm holding my hand. So into the page or into the camera. One small thing to be aware of, though. The right-hand rules are designed from the perspective of positive charges and protons, kind of like how most electricity is. And that means that for an electron, you'd actually need to reverse the answer. So, whatever direction a field would push on a positive charged particle, it would push in the opposite direction on a negatively charged particle. So, here, instead of pushing into the page, it would push out of the page. For C, we've got velocity to the left and field to the right. Those two aren't perpendicular to one another. They're not perpendicular. There's no perpendicular overlap here. So there's just not going to be any magnetic force present in this specific example. The formula would give you a 0 because no part of the velocity is perpendicular to the field. No part of the field is perpendicular to the velocity. For part D, the field is at an angle, which means only some of the field is perpendicular to the path, to the velocity vector. Now, if we divide this vector, the field vector into its components, it would have positive y components and positive x components. The positive y components aren't going to exert any force on a particle that's moving in the positive y direction. So only the positive x part of this field is going to exert any force, and that's the only part we really care about right now. There's some field pointing in the positive x, that's going to be what exerts force on the particle moving in the positive y. So if you take your hands and just hold it up to the screen, we've got particle velocity pointing with your pointer finger. The field velocity is going to point in the positive x, and so that means that our resulting magnetic force is going to point into the page. So that's an X for into the page. This is allowed to be weird. It's a strange concept. It's certainly kind of weird to have to be moving your hand all over like this. So we'll call our break for the day to let this settle in to your mind. We'll pick back up with it tomorrow, kind of look at some more examples, make sure that the concept makes sense before we start doing the math, before we start showing where this is used, like what it could be used for, where it occurs in nature. But before we officially end for the day, I want to show you why it's important, why this is an important thing that happens in nature. This picture particularly represents solar radiation and charged particles from the sun blasting out towards our planet and our magnetic field blocking the bulk of that radiation and charged space debris. The sun is constantly sending out charged ions, charged particles towards our planet, in addition to some other things. And if all of those superheated particles made it to Earth's surface, life on Earth would be pretty bad. That'd be a lot of charged ions just bombarding the surface all at once. Life on Earth wouldn't really be possible. That's why Mercury is uninhabitable. The sun side of its planet is constantly being bombarded every single day because it doesn't have a magnetic field to protect it. Earth does have a magnetic field. And so when those charged particles from the sun enter Earth's magnetic field, remember, Earth's field points from the South Pole it points from one of the poles to the other. So from this angle, the velocity and the field lines are perpendicular. Earth's magnetic field exerts a force on those incoming charged particles. And specifically in this case, it would... it would actually direct, in this specific case, it would direct the particles out of the page from this particular perspective, sending them away from the planet, sending all of that charged space dust away from Earth's surface. This keeps us safe. This is one of the things that makes Earth a habitable planet, as opposed to Mercury, which has no magnetic field, and so it's constantly being bombarded every single day by radiation and space dust from the sun. We haven't really sent any probes to Mercury because they would melt. So, literally, this right-hand rule stuff is happening every single second of every single day, protecting us from excess amounts of energy from the sun. Our magnetic field is very specifically tuned to allow in just the amount of energy we need to make Earth habitable, which is pretty cool in my opinion. And as a consequence of this, when the charged particles hit our magnetic field, they tend to leave some of their energy behind. It's like literally slamming into a force field. That energy energizes air in the atmosphere, and it creates auroras. So the energy runoff from charged particles hitting our magnetic field energizes the atmosphere around the poles, and that creates the aurora borealis and the other aurora at the other pole that I don't remember the name of. So, pretty important to everyday life on Earth, and pretty important to creating one of Earth's natural wonders. So, we'll break here for today. That was probably a lot of information to have to digest. So, as always, let me know if you have any questions or any needs, concerns, what have you, etc. We'll break here for today. I'll be in the call for the next hour. If you hop back in with questions, just let me know. And if I don't see you again today, I will see you tomorrow for even more magnets. Take care.